All right, in this video, I'm going to cover 7.3.4 Bootstrap standard error, and we'll see examples of Bootstrap problems. Okay, so let's see. So what is the Bootstrap? The Bootstrap is actually a numerical method to find um, what the standard error, the estimate of standard errors. Okay, so now we'll see. So in generally the bootstrap, yes, I told you numerical method or computer intensive technique, or you can say a numerical method to calculate the estimator of sample statistic. But here I'm going to cover the estimator of the standard error. Okay, so suppose that excuse me. So suppose that we have a random variable x with PDF f of x and the parameter data. So let's see. Oh yeah. Give me a second. Yeah, let's see PDF f of x and the parameter data, and then we assume that um, we have the random sample of a size n, so x1 through xn. Keep in mind this x1 through xn are considered as what random variables, right? So now see, they assume that the estimate of data. So data is a parameter, okay? So we want to estimate data based on the sample data, okay? So then data head is a 4.5, okay? So this is the estimate of data. And now here's a bootstrap procedures, okay? So the generate bootstrap sample randomly from the PDF f of x with the data is equal to data head. So since we do not know the parameter data, okay, so we use a sample statistics data head 4.5, which is estimated data, okay. So now using the PDF, then we can generate the sample random. The random sample boost is called the bootstrap sample, random sample, and they calculate the bootstrap estimate data head B. Okay, so in the step 3, repeat this process NB times, okay, resulting in. So you see, bootstrap sample 1 is just say x11, x21. So these are actually the random sample data generated by Bootstrap. Okay, so now that we can calculate the 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 sample statistic data head, right? So that is called Bootstrap estimate data head 1b. Okay, since we generate the the Bootstrap sample random, the random sample NB times, see? Okay, so right, the NB times. So we have NB, um, the NB, Bootstrap random samples. Okay, so now let's see. So the Bootstrap sample 2 is x12, x22. So subscript means the index of sample data, and the superscript represent the bootstrap sample number. Okay, so in this sample bootstrap sample data, we calculate bootstrap estimate data head to be. Okay, so now keep doing this. Okay, finally we got this bootstrap sample NB, NBth sample bootstrap sample. Okay, so we got the data head B and B. So now what are you going to do? So using, we collect all the bootstrap estimate data head B. Okay, so by the way, the number of the bootstrap sample is going to be 100 or 200. Okay, the sample mean bootstrap estimate. So we're going to find out the mean of the that bootstrap estimate. It's called the sample mean bootstrap estimate. Okay, so 1 over the total number of the bootstrap sample, which is n sub b, the sum of all of the bootstrap estimate. Okay, then we calculate the bootstrap standard error. Standard error is actually standard deviation, right? okay, standard deviation, called denoted by SE in the data head, which is square root of 1 over MB minus 1, and then sigma data IB head. This is Bootstrap estimate. I mean, uh, the Bootstrap estimate in the I Bootstrap sample, right? Minus data head B. So data head B is a sample mean Bootstrap estimate. Okay. So now in the so that's the SEB and the data. This is the standard error. Okay. Generated by Bootstrap. Okay. So now see example 7.5. So give me a second. Let's see. All right, so this is example 7.5, Bootstrap standard error example in textbook. So see, a team of analytics specialists have been investigating the cycle time to process loan applications. So the specialists' experience with the process informed them that the cycle time is normally distributed with a mean of about 25 hours. So a recent random sample of 10 applications gives the following. So this is the sample data is sample right there. So now the sample standard deviation of these observations. So from the 10 observations in sample, we can get what standard deviation, right? 3.11407. That's going to be beta head. Okay. So we want to find the bootstrap standard error for the sample standard deviation. So we use a computer program to generate MB, setting MB at 200, and the bootstrap samples from a normal distribution with a mean of 25 and a standard deviation of 3.11417. You see that standard deviation of 3.11417? That comes from what? The sample, excuse me, sample standard deviation. Okay. All right. So now we know the f of x, right? PDF, because problem says that what the population. Sorry, the what? Uh, we used the problem size to the bootstrap sample from a normal distribution. Right, normal distribution. So we know the PDF of normal distribution. We learned it, right? The first of these sample is this. Okay. So now let's see that. Okay. And then from which we calculate as 2.50635. Okay. So that's the bootstrap estimate of standard deviation, sigma actually. Okay. Generated by the bootstrap. Okay. So now the yeah, how can you generate the bootstrap sample? Yeah, we need the problem says we use a computer program. So um, the here we don't have you don't have to get a computer program to generate bootstrap. Okay, so we don't have to do that. So that's the beyond of this subject. So we definitely problems give you the certain samples so that we can calculate the bootstrap estimate. Okay, so normally you don't have to do step one in bootstrap procedure. So after all 200 bootstrap samples were generated, the average of the bootstrap estimate of the standard deviation was 3.03972. So that's the bootstrap. I mean the sample mean of the bootstrap. Okay, estimate. And then the bootstrap estimate of the standard error is this. We know how to calculate this, right? So that's the what? This is a square root of what? 1 over MB minus 1 times the sigma, and then, bootstrap estimate minus the bootstrap sample mean square. Is it? Okay. So now, let me see. So, okay, give me a second. All right, so here we're gonna see the exercise problem, online homework problems. Okay, so give me a second. So this is a problem assignment chapter 7.1 through 7.4, and then research problem 7, chapter 7, section 3, problem number 10. So see, here's the problem. An exponential distribution is known to have a mean of 10. And then you want to find the standard error of the median of this distribution. So if a random sample of size 8 is drawn, okay, in order to use the bootstrap method, and so B is 5, and the bootstrap samples are generated. So as I told you, so problems, you don't have to do step 1. So they're going to give the bootstrap samples already generated. Okay, so you see that sample 1, 2, 3, 4, 5. There are 5 bootstrap samples generated and then given in problems. So what are you going to do? We have to find out what the bootstrap estimate, right? Here, what we want to do, we want to estimate what the population parameter. Here, the population parameter, what we want to find out, the estimate is what? The median, right? So then you want to find the standard error of the median of this distribution. Okay, so now median, that's the population, the parameters. So we want to find out what standard error, standard deviation of the what sample, what bootstrap, bootstrap the sample median. Okay, so what we're going to do, we have to do is we have to find out sample, bootstrap sample median for each samples. Okay, bootstrap samples. So see now, that's step 1. So definitely you have to enter all the samples in the calculator. So we learned that in a statistic 1 class, right? So go to press stack, right, and then go to the edit, press edit. So I already enter the first 3 samples. Okay, so but please enter the all of samples data. Okay, so now what we're going to do, we're going to find out the median for each sample. That's going to be bootstrap sample median. Okay, so once you enter all the data, sample 1 through sample 5, then we go to the sample, press stack again, and then go to the calculus. You see that calculus tab right there. Okay, and then we do one variable stack, because one variable stack gives us this basic summary of statistic of that sample data. Okay, so now click here, and then I enter the L1. Okay, so L1, and then skip the frequency list. Okay, so calculate. Then you see there is a median, right? See 9.11. Okay, so now store 9.11 into the other list. What I mean is just go to stack and then press edit. For me, I just enter the 9.11 into L5. Okay, so similarly, you find the median for sample data 2, sample data 3, sample 4, 5. Okay, so then the enter all of the median in L5 or other list. Okay, calculator. So I just store, and then you're gonna find out what. Now we find out what standard error. Okay, bootstrap standard error, which is what? That's nothing but sample what? A sample standard deviation. Okay, so now we're gonna calculate the press stack right there. Go to calculate, and then one variable stack, and then press 1 L5. Now we calculate, then you see the SX right there. Okay, see that? That's the sample standard deviation. Do not confuse with the sigma x. This is the population standard deviation. Okay, so because what we are dealing with what samples, right? Sample data. So don't put sigma x. Okay, even we know what's the difference between sample standard deviation and population standard deviation, right? For the sample standard deviation, we divide by n-1, right? So the sigma x, a population standard deviation, we're gonna divide by what? The total number of the data in same population, right? So okay, so the answer is 3.29, but rounding up, then we're gonna get 3.3. Okay, so that's why Answer is 3.3. Okay, so so please look at the Bootstrap procedure in the lecture note. Okay, so and then following that steps, except for step 1, okay, then you can solve the online homework problems. Okay, so now next one is the right here. Okay, so now we'll see. We saw example 7.5, right? So, but let's see. Mm, give me a second. Yeah, so please look at the example 7.5. Okay, so this is I just summarized the problems in 7.5, example 7.5 in the textbook, because I explained by looking at the textbook. So let me skip it. Okay, and then let's find out if there is more problems I can cover in our online homework set. Give me a second. Okay, let's take a look at the chapter 7, section 3, problem 7 in the online homework. So so let's see second question. Okay, first, under which condition data 2 head is more efficient than data 1 head? By the way, sorry, let's take a look at uh, the assumption. Okay, suppose that data 1 head and data 2 head are estimator of the parameter data. We know that uh, the expected value of data 1 head is data. What does that mean? Expected value of data 1 head is data. It means that what data 1 head is unbiased estimator, right? Because you know, remember that bias. How bias is calculated by the what data expected value of data 1 head minus data. So in this case, I mean, in the case of the data 1 head, bias is 0. It means that data 1 head is unbiased, unbiased estimator. Okay. And the expected value of data 2 head is data over 2, and the variance of data 1 head is 15, and the variance of data 2 head is 4. So now back to, yeah, now we see our second question. So efficiency, to calculate efficiency, so then, yeah, I didn't cover this one in the in the textbook lecture note, but let's see. Share here. Okay, so we use that formula. The relative efficiency is that is defined by the variance of data 1 hat plus bias of data 1 hat square, and then data variance of data 2 hat plus bias of data 2 hat square. Okay, so now let's see. Okay, now I'm gonna plug in numbers. Therefore, we have to find the bias of data 1 hat, bias of data 2 hat, and then okay, and then we're gonna plug in numbers into the formula. Okay, so now the variance of data 1 hat. See, variance of data 1 hat. The problem says the 15. The variance of data 2 hat is a 4, right? And then bias of data 1 hat, that was what? This is equal to expected of data 1 hat minus data, right? This is 0, right? Because data expected value of data 1 is data. And the bias of data 2 hat, that's going to be what? Data over 2 minus data. This is what? Minus data over 2. Okay. So now, then this is equal to, now, so the relative efficiency, yeah, that is equal to what? The variance of data 1 is what? 15, right? So 15 plus 0 square. Oops, not the data. Okay, this is 0. Oops. Over, and then what? The variance of data 2, which is 4, right? 4 plus, and then minus data over 2 square, right? Which is 15. Okay, over 4 plus theta square over 4, right? So let me simplify this. Okay, so then let me divide multiply by 4. Okay, so 60 over 16 plus theta square, right? Okay, okay, so look at the question. What's the question? Under which conditions data 2 head is more efficient than data 1 head? Okay, so give me a second. So here, in order to the theta 2 head is more efficient than theta 1 head, then this guy, I mean, what? Give me a second. So the denominator must be what, less than numerator. Okay, if a numerator is less than denominator, that means theta 1 head is more efficient than theta 2 head. But the problem says that under which conditions theta 2 head is more efficient than theta 1 head. Okay, then it means that we have to find out the range of theta where this guy is what, the gradient. Okay, and then normally we put the equal sign. Okay, normally put gradient. Yeah, so gradient 1. Or other way, just find out this. Just solve that inequality less than or equals 1. Okay, it means that we find out the range interval where the what, theta 1 head is more efficient than theta 2 head, and then we're gonna find out the what, the complementary of that interval. Okay, well, let me do this way. Either one just fine. Okay, but it's key in mind is if the numerator is what, a less than denominator. Okay, it means that this fraction is less than or equals 1. That means theta 1 head is more efficient than the theta 2 head. Okay, and then reverse of that inequality, that means what, theta 2 head is more efficient than theta 1 head. But let me solve that inequality. Okay, then all right, so now here, then 60 is less than or equals 16 plus theta squared, right? Okay, so 44 is less than or equals theta squared, right? Okay, so now that means what, theta must be between what, the negative square 44, right, and then positive square 44, right? Okay, so what does that mean? It means that if theta is if theta is between negative square 44 and square 44, theta 1 head is more efficient than theta 2 head. But that's not what we want, right? We want to find the what, opposite. We want to find the interval where interval of theta where theta 2 head is more efficient than theta 1 head. So with the answer is what, theta let's see, give me a second. Theta 2 head, yeah, this is wrong, right? Sorry. If you solve this, theta is less than or equals negative square 44. Okay. Or theta is greater than or equals square 44. I'm sorry. Okay. So opposite of this is what? Square negative 44 and then square 44. Okay. So that's the answer. Okay. Well, opposite, there is no equal sign, right? So opposite of that in interval is this, right? Sorry. Okay, so equal sign should not be included, right? Okay, so if theta is between square root negative 44 and the square root 44, then theta 2 head is more efficient. Okay, so that's the I didn't cover that. And then let's see, just give me a second. Let's see. Yeah, let's say the first question. So which estimator is better for unbiased? Definitely what, the what we have to choose, find the estimator whose bias is what, 0 or almost 0, right? The least, I mean. So theta 1 hat, right? Because why? Because the bias is 0. So the answer is theta 1 hat. Okay. So now that's for this video. Okay. Next video, I'm going to continue to cover 7 point what, 7 point the last part of 7.3 and then 7.4.